Hey everyone, welcome back. On behalf of Forge College, I am just absolutely thrilled to have you here for another explainer. So if you've been following our track on transitioning from EVM to SVM, you probably remember that in our last lesson, we conceptually mapped token primitives from Solidity over to Rust and Anchor. We talked about ownership models, balances, and metadata, but mostly on a theoretical level. Well, today it's time to actually get our hands dirty. We're diving into the exact, concrete implementation of token storage and account layouts in Rust and Anchor. Now, if you're coming over from Ethereum, let's just be brutally honest for a second. In Solidity, storage is basically magic, right? You define a mapping, you throw some variables into a contract, and the Ethereum virtual machine just kind of handles it. It dynamically expands, it does its thing, and you almost never have to think about the physical bytes. Well, welcome to Solana, my friends. On the SVM, we don't do magic. We do math. Exact, relentless, space-calculating math. Because on Solana, token state is persisted inside explicit accounts, and you literally have to pay rent for the exact amount of space you take up. So here's our engineering blueprint for today. We're going to cover 1. Drafting the vault, 2. Defining the account struct, 3. Calculating rent space, 4. Deriving PDA seeds, 5. Initializing token state, and finally 6. Testing the blueprint. Let's get right into it.
All right, section 1, drafting the vault, specifically looking at anchor account structs.
So what exactly is an anchor account struct? By definition, it's a typed Rust struct that Anchor automatically serializes and deserializes to persist your token state on chain. Remember all those primitives we mapped out last time? The balances, the owners, the metadata? Well, they can't just float around in the ether. They need a concrete physical container, right there on the Solana network. The Anchor account struct is that container. Think of it as a literal mold that shapes exactly how your token data sits on the blockchain.
Moving along to section 2, defining the account struct and figuring out its exact physical dimensions.
Now, what is really fascinating about this breakdown is how every single field has a strict, predetermined byte size mapped out. We're not just saying, hey, here's some data. No, we are defining exact physical dimensions. We've got an 8-byte discriminator from Anchor, a 1-byte version tag, 32 bytes each for the mint and owner public keys, an 8-byte slot for a 64-bit integer balance, 1 byte for a Boolean approval flag, a 64-byte metadata blob, and 32 bytes of reserved padding. Every single piece of data is meticulously accounted for. There's zero guesswork here. Now, looking closely, you might have noticed we used a fixed 64-byte limit for the metadata instead of your standard string or dynamic vector. Why? Well, because dynamic arrays, like a vec in Rust, they completely ruin our perfect space calculations. If you use dynamic arrays without explicit length prefixes, your account size can unpredictably grow. And on Solana, unpredictable growth leads to absolute chaos and runtime errors. By utilizing a fixed-length byte array like U864, we guarantee that our vault's dimensions will never suddenly bulge out of its designated plot on the blockchain. It stays exactly the size we want it. Okay, section 3, calculating rent-exempt space. Let's talk about the exact space required. To calculate our required space, we absolutely always have to start with the number 8. I literally cannot stress this enough. This is Anchor's famous 8-byte discriminator. Think of this as the mandatory, unskippable building permit fee that Anchor slaps onto the start of every single account it manages. It's exactly how the Anchor program identifies that, yes, this account actually belongs to it and matches the specific struct you defined. Forget these 8 bytes and your entire construction collapses before it even begins. Seriously, don't forget the 8. So when we take that 8-byte discriminator and we add up all our other field sizes, the 1-byte version, the two 32-byte pubkeys, the 8-byte balance, the 1-byte bool, the 64-byte metadata, and those 32 bytes of reserved space, we get exactly 178 bytes. This is the magic number for our specific vault. Honestly, it's highly recommended to implement a small helper function right in your Rust struct, something like space, that just returns this 178. That way, you have this single authoritative source of truth for sizing whenever you go to initialize the account. Which brings us to section 4, deriving the PDA seeds. Time to find our deterministic GPS. So with the size strictly locked in at 17 8-bytes, where do we actually put it? We need exact deterministic coordinates, which brings us to PDAs. A program-derived address, or PDA, is an address that's deterministically derived from a set of program seeds and a mathematical bump. The truly incredible thing about PDAs is that they act as a secure vault without needing a private key. Since no private key exists for this address, only your program can mathematically generate the signature for it. It absolutely guarantees that we can always locate our accounts safely, and it enforces really strict authority rules right at the Solana runtime level.
So, how do we actually formulate this address? We use an exact PDA engineering formula in our anchor account seeds constraint. For our token state, we are going to use 3 seeds: the literal byte string token, followed by the token mint's public key, and then followed by the owner's public key. By structuring it exactly this way, we're permanently mapping a specific owner to a specific token mint. If I want to find your exact balance for a specific token, I just hash these 3 exact seeds together, and boom, I instantly have the precise GPS coordinates of your vault. It's brilliant.
All right, moving into Section 5, initializing the token state and actually executing that initialization.
So here's what the initialization handler's workflow actually looks like in practice. First, Anchor computes the 178-byte space via our handy helper function. Second, it derives the PDA using those exact seeds we just discussed. Third, Anchor automatically validates all constraints, ensuring that the correct pair is signing and that the PDA is derived from the right program. If all of this matches up perfectly, Anchor actually performs the cross-program invocation to the system program to carve out the account for us. It automates all the heaviest lifting, provided we give it the perfect parameters. Then, once Anchor has successfully carved out that perfectly sized rent-exempt space at our PDA, it hands control over to our Rust handler function. And this is exactly where we step in to assign the initial starting fields. We set our version tag to 1, we populate the default balance to 0, and we set our approved flag to false. The space is built, and the default data is now locked securely inside. Finally, Section 6, testing the blueprint to ensure structural integrity. A master architect never builds a structure without inspecting it first, right? So let's run our final checks before deploying to the live network. And this really brilliantly illustrates the power of Anchor's local testing environment. We start simply with an Anchor build to make sure our Rust types and macros compile without throwing any errors. Then, we write a quick unit test to verify that our space helper actually spits out exactly 178 bytes. Next, we test that deriving the PDA off-chain precisely matches the address our program initializes on-chain. And finally, we fetch the account and verify the default fields, like balance and version, are correct. Running these deterministic checks locally absolutely guarantees our token storage won't just buckle and fail when it's exposed to the wild on-chain environment. Now, a super quick troubleshooting note. What happens if you test this and you get the dreaded account data too small runtime error? Look, this is essentially a rite of passage for Solana developers, so don't panic. If you see this, stop and check 2 things. Number 1, did you forget to include that 8-byte anchor discriminator in your space sum? Or number 2, did you accidentally sneak a dynamic vec into your struct instead of using a fixed-size byte array? Fix those 2 things, and I promise you the error will vanish. And before we wrap up, I want to drop a really crucial pro tip about migration safety. Notice how we explicitly added a version field and a 32-byte unreserved array in our struct? Well, in the immutable world of blockchains, you can't easily change the size of an account once it's already created. But by adding a reserved byte array right now, you give your token state some breathing room to expand later on. If you decide you want to add a new feature next year, you just eat into those reserved bytes without breaking the 178-byte deserialization structure for older clients. It is literally the ultimate future-proofing hack. So, look what we've done. We've successfully mapped our storage blueprint, we meticulously calculated our exact byte spacing to remain rent-exempt, and we safely initialized our PDA vault. But, an empty static vault isn't very useful, is it? Now that our vault is solidly built, how do we actually move the tokens inside? How do we handle transfers and approvals? Well, that is exactly what we are going to be tackling in our next explainer. To master the rest of this transition from EVM to SVM and to dive even deeper into these concepts, be sure to visit forge.college. It's been an absolute blast breaking this down with you today. Keep building, keep testing those blueprints, and I will see you in the next explainer.